to all of our guests this afternoon. Thank you, everybody, for joining us for the ACE webinar series. And I'm really pleased that Murray Gibson is able to join us today and share some of his experience. So Murray is the founder of Saturn Ergonomics, and that is in Auburn, Alabama. You might get a little bit of that from his accent. Sorry, Murray, you're talking to a whole bunch of Canadians here. We might pick up on that accent. And Murray's a licensed professional engineer and also a CPE, a certified professional ergonomist, with experience at the plant level, corporate level, and as a consultant to over 150 companies. And Murray is also the co-author of the recommended Cumulative Recovery Allowance. Easy for me to say. That's why we always call it the RCRA, with Dr. Jim Potvin there, who we just heard a little snippet. Hello, Jim. So Murray's going to share a multitask evaluation with the RCRA. And as you kind of heard there, Murray is a PhD student in the Department of Industrial and System Engineering at Auburn University, and getting close to dissertation time and presenting. So good luck with that. But before you get on to that, you have to share with us a little bit about multitask evaluation with the RCRA. I'll turn it over to Murray from a presentation standpoint. You all know we're using Zoom these days. You could unmic yourself to ask a question, but what I'm going to ask is, during the presentation, do you want to use the group chat, please, and send questions or anything, and then I'll interrupt or facilitate. I shouldn't call it interrupt. I'll facilitate questions with Murray, and we will leave some time at the end for questions. So right now, through the presentation, we'll do it by written chat form, and then at the end, we'll open it up and you can unmute yourself and we can have a nice discussion. Okay, so without any further ado, Murray, I'll turn it over to you.
Okay, thanks, Allison. Yeah, I'm in Auburn, Alabama. You can probably pick up the accent's a little bit different, the southeastern accent. I've gotten pretty good at picking up Canadian accent right here. Little subtle things like a boot, instead of about, how I would say it. But there's so many, what I've realized, there's so many savvy ergonomists from Canada, and it seems like more and more of my ergo friends or people I interact with or Canadian ergonomists. And so, and I went in 2017, Jim invited me to the conference in Banff, and anyway, I was just astounded at the level of knowledge of the Canadian ergonomist. And kind of what comes to mind is they talk about the Masters golf tournament, the fans, the most knowledgeable gallery in the world or whatever. But like I was saying, it really astounded me that there's such a high level of knowledge of practitioners. But anyway, I'm looking forward to sharing some of the things I've learned applying the RCRA, and some things that sometimes don't work, and I've come up with some solutions and even ideas for future application. I'm an industrial engineering background, so I kind of have a engineering-based view of the world, and I've grown to appreciate the Canadian, the work physiology and biomechanics, and a lot of the strengths. And it's almost a lot of the stuff I find myself reading more and more papers that are by Canadian researchers. But anyway, it's kind of a interesting combination, I think, apply some of the maybe US engineering-based ergo with some of the skills of the Canadian ergonomists. It kind of results in some neat things. Kind of the mission, when I consulted for several years for many different companies, but I was never really satisfied with the tools that we use, the analysis tools. And I really wanted to create more innovations to help practitioners. And so we could be more effective applying ergonomics. Here's where I am in Auburn, Alabama. I haven't been at my office as much lately as normal due to COVID-19, but I'm very close to the Auburn University campus. And typically I have anywhere from sometimes just 1 or 2 students, but I've had as many, sometimes in the summer, 5 or 6 students helping me working for me as interns working on projects. And I actually have some interns now that work. One particularly works full time, but it's neat to see these students. So they go into Apple and Google and different places, work for NASA. Um, but here's sort of an outline. I want to talk about the kind of intro to the RCRA. I want to provide a detailed example. One thing that irks me a little bit is sometimes I hear, well, it's difficult to apply. And I try to think of it from the standpoint of someone who's not as familiar with it as I am. So I'm going to cover some of the things that I think people might be a little intimidated with, and hopefully make it easier to apply so that more people will be comfortable using it. But I've learned sort of through application where some of the difficulties you run into, or where the metrics tend to break, and I'm going to share some ideas, show some new metrics. Also talk briefly about some application barriers and future applications. So the RCRA, Recommended Cumulative Recovery Allowance. One of the fundamental things to know, even before we get started, is duty cycle, to have a solid understanding of that. And for example, if looking at the pie chart, if you have the muscle activity, if the muscle's active for 22% of the time, and it's inactive for 78% of the time, your duty cycle would be 0.22, 22%. Here's how you would calculate duty cycle. If you look at the lower left-hand corner, you see you have a 1 second duration force, you have a 2 second duration force, and then you have another 1 second duration force. Well, if you look at the calculation for that, 2 times 1 second plus 1 times 2 seconds divided by 10 seconds, so it's 0.4. But that's basically how you calculate duty cycle. So wherever those forces occur, is the percentage of time that you're applying force. And what's interesting, this is from Dr. Poppen's MAE paper, but if you look at force versus frequency and what the acceptable limits are to people, it's sort of all over the place. And Jim was smart enough to figure out that if you put it on the common denominator of duty cycle, for example, if you look at those studies, some of the durations might have been 1 second, some might have been 3 seconds or 5 seconds. But when he normalized it for duty cycle, you see a nice curve and had an R squared 0.87. And that was in Jim's MAE paper, 2012, I believe. And this is the MAE equation, 1 minus duty cycle to the 0.24 power. So that duty cycle we were just talking about, it plugs right into the equation and tells you the percentage of your maximum effort that people can apply without experiencing undue levels of localized muscle fatigue. And an example of the MAE, say we have our 0.4 duty cycle, and you can look on the chart. If you go up where it intersects with the curve, it's at 20% of the maximum acceptable effort. So our MAE is 0.2. What does that really mean? Well, what it means is under those conditions, a person could apply 20% of their maximum strength without experiencing unacceptable levels of localized muscle fatigue. And this would be a single task profile. I'm going to talk some about single task and multitask evaluation. Over the last couple of years, I've really grown to appreciate the advantages of multitask evaluation. But when we use a single task model, it almost like we have to make it fit, like everything's a single task. And when people do work, it's multitask. But a single task model assumes there's a constant level for force, for posture, and for duration, and you plug that into the model. But the jobs, when we look at real jobs, we have forces of different magnitude. You have some high forces, some low forces, some forces of long duration, some of a short duration. So with a multitask model, that allows us to do is we get much closer to simply what we observe and measure. We can plug into the model and we can get an output. And more importantly, we can see what specifically needs to be fixed. What's the priority priority task that we need to fix? But typically when we try to use a multitask model like the strain index or ruler or some other single task model, when there's a multitask force profile, what we wind up doing is a lot of times in the papers themselves, they'll recommend, well, just we use the word err on the side of caution and use the worst case. What happens then is we tend to overestimate or overvalue the risk. It gives it a rating that's too high. If we use the average, what it tends to do is undervalue. And this is because even some of the with the RCRA and even the Auburn University fatigue failure models, what we're finding is the higher force exertions that really rack up the metric. It's typically the higher forces with RCRA you're going to have play a much more significant role in determining the metric than some of the lower forces. So the high forces are very important. But every force has a requisite recovery time. And this is kind of a little simple way to look at this. We have a force of a duration and a magnitude. So what if we kept the same duration and we had a higher magnitude? We would have it would take more time to recover. Okay, if we go back to that same situation, what if we kept the magnitude constant and we increased the duration? It's going to require more recovery time. So what I got interested in, and I think I was on vacation reading Frederick Taylor's The Principles of Scientific Management, and how this is back, over 100 years ago. He was trying to get more productivity out of jobs, but one of the key examples he was using in that book, it was actually a conference paper, but one of the key examples he was using, he was trying to figure out how much recovery time was necessary so the workers didn't get fatigued. He was noticing toward the end of the second half of the shift, he just wasn't getting any productivity out of people. So he wanted to pace the work, and he wanted to calculate, after you apply force for a certain duration, what's the recovery time. And then remember, a few weeks later, I was reading in the Kodak book, Sue Rogers was using the Roman equations to try to do a similar kind of approximation. It was more, organized than Frederick Taylor's version. But then, so I was thinking, okay, decided I would like to build a fatigue evaluation model. I got looking at different kinds of fatigue and realized, well, like cognitive fatigue, it's kind of difficult to wrap your arms around. Whole body fatigue, energy expenditure, that's kind of a whole separate area of fatigue. But I got really interested in localized muscle fatigue. And I've always been interested in measuring forces. And it seems like I've always been when I worked with a consulting firm, I was the go-to ergonomist. If somebody had a question about force, what was acceptable. So I wanted to build a model or develop a model to determine if we know the force magnitude and the duration, how much recovery time would be needed. And I was about to give up in my effort to do that. And I had read through the textbooks that I had, and I had probably 30 papers or so that I looked through. And it was literally, I think it was the last paper, it was Dr. Poppins' MAE equation. And when I saw that equation, it was like, wow, it's in there. I know that I can tease out of that equation what I was trying to find. And so what I did is, after about a page or so of by hand with algebra substitution, derived the RCRA equation using Dr. Poppins' MAE equation. And then subsequently, it wasn't long after that, I presented that at the Applied Ergonomics Conference in Orlando, Florida, and met Jim. And it was, to share with you too, I'll never forget, I was kind of apprehensive about presenting the model, because I was like, I'm not a PhD, who am I to present a new model or whatever. And then I looked up and I saw Dr. Potvin coming in there, and I got nervous. I was like, wow, he's actually here. The guy had built he's one of my favorite researchers that I always, tended to follow his research, and he was actually there. But here's the RCRA equation. And if we look at these, I'm going to work through kind of a detailed example in a minute. Initially, I'll do kind of a rough one so you kind of see the big picture. But you have recovery time per cycle, and then you have the duration of each effort, the effort frequency, the number of times you apply force during a cycle, and the known effort expressed is a percentage of maximum strength. I think this tricks up some people every now and then. And then there's a kind of a little additive component in there that Jim and I put our heads together thinking about, okay, we're going to give some allowance if you have to occasionally apply a high force for a short duration. So that's what the DC min does. It assumes that you can do 100% effort for 1 second every 8 hours. And sometimes I think Jim's even using a higher DC min now. Typically, I don't use the DC min in my calculations. So it'd be a little bit more conservative. But this is the basics of the RCRA model. You have the magnitude, the frequency, and the duration of the force. In the output, you have the recovery time. Okay, and this would be an example. This one, you can see we have a 20-pound force, two 7-pound forces, and 11-pound forces, and the forces are different durations. And I'll notice between the forces, this would be for hand grip force, between the forces you have when the muscle is inactive, so it's not applying that grip force. So you have 39 seconds of time that's in task recovery, but the other duration, the force is being applied. Now, if you did the RCRA calculations, I believe this was using 10th percentile female capability, but you see for each force, there's a count, there's a duration, and then there's a recovery time, and you total those up, and you sort of get what I would call model recovery time. And then a ratio, this is one of the ratio that typically is applied. You take the ratio of the model recovery time to the actual recovery time. And in this case, it's slightly over 1. And what that means is you have enough recovery time in the cycle to recover from those exertions. So each one of those forces, we calculated how much recovery time you would need to recover from that. And then we compare that to that 39 seconds that's already in the cycle. And anyway, that's kind of like similar to the NIOSH lifting guide as far as the color coding. If it's less than 1, there's enough recovery and it's green. And at some point it gets, if it's 2.5 or 3.0, it would be red. Okay. Now what's really neat, more than the metric, is I found solving the problem. Just about everything in the world follows Pareto. If you'll notice, yeah, just about anything. It could be, what you spend your money on, or things that are cost, or in this case, things that contribute to our metrics, things that cause where you rack up the need for recovery time. Usually it's a subset of all the tasks. If you list all the tasks that are in a job or a station, it's almost always a subset. It's usually 1, 2, or 3 of those things that's your primary problem. So what this enables you to do, this is what the single task models couldn't do, but this can allow you to focus, okay, out of all these things that the worker does, we need to focus on this number 7, this number 10, and number 11, and fix those things. And we don't, we can, if we make an improvement to one of those other items, we can certainly, every little change you make just trickles through the metrics and is reflected in your resultant metric. But which things make up the lion's share of your metric or your resultant metric. And this is what's neat too. There's different ways you can look at it. You can look at very complex jobs. I was looking at one job I looked at had 19 different tasks, and it was actually shelf locations. And we came up with a way to look at all these different locations. But this is the example here. We have 11 tasks, and you can see tasks 1, 5, and 11. That's where the lion's share of the problem is. Okay. And also, you can do things like, if you get creative, okay, let's look at item weight. Maybe they have all these different locations, but we can sort it and look at by item weight. And here you see, oh wow, that top tier of the weight classification where we really rack up the metric. And I remember this particular another job, I remember there were certain locations, and we did a kind of a graph of the location and the item weight. And I was like, wow, holy smokes. So we knew exactly what we needed to fix. And it makes it much less intimidating when you can go in sort of a rifle approach and develop your solutions, knowing that that's going to impact the metrics. I'll go through kind of a more detailed example. Okay, we have a job that requires 2 power group forces over a 24-second cycle time. Okay. So you see the data there, and let's calculate the RCRA ratio. Okay, one of the things, Okay, first you've got to have your population strength data, the mean and the standard deviation. And you need at least a basic knowledge of the normal distribution. And I typically design or evaluate for the 25th percentile female for strength. So we have a z-value. If we take that mean plus minus 0.67 times our standard deviation for female power grip 13, so you can see where the 63 came from. But anyway, that's how you get the 25th percentile female strength. So that would be a value that 75% of females would be that strong or stronger, and almost 100% of males. So if you set it at that level, pretty much all, until you factor in your industrial workforce, it's probably a little bit stronger. You've got a fairly protective limit there. But that's a good place to start. But this shows how, okay, we take the magnitude force, let's just do force 1, magnitude of 22 pounds, the duration of 2 seconds. And you see the equation and you see the variables, but this E, known effort expressed as percent of maximum strength, I think that's where some people get a little confused. Notice that 22 pounds, that's the actual force divided by that 53.2, see down in the lower right-hand corner. I'm sorry, I put the wrong number in there. I'm sorry, 54.3. But that's your E value. In this case, E is 0.405. So don't let that intimidate you. That's just your population strength. Now, if it was a pinch grip, maybe we're looking at a lateral pinch or tip pinch, it'll have its own mean and standard deviation, and you can you evaluate that accordingly. But that's where the E comes from. If you see at the bottom, I plugged in all those variables. We have the duration of each effort. For force 1, it was 2 seconds, and our frequency was 1 time per cycle. And then you see the DC min, and then you see the 0.405. So relatively straightforward how you do the calculations. Then you subtract the duration of the effort times the frequency, and you get 15.4 seconds. So that tells you for that force 1, you need 15.4 seconds for the muscles to recover. Okay. And if we put it in a table here.
Hey, Murray, there's just a question just to clarify it. So E is a fraction and not a percentage. Is that correct?
It is a, right, that's correct. It's a fraction. But now one of the things that was frustrating early on applying the RCRA is you would get an infeasible calculation. And that's if your force actually exceeds that population strength. Say if I had a 75-pound force, it won't calculate because you're taking anyway, it just is not feasible. And so, but if you think about it, like if I could bench press 200 pounds, and if you ask me to bench press 250, it's not feasible. So the calculation breaks. And I've got a metric that I'll introduce in a minute that sort of takes that into account. And another problem is inflated metrics. Like you'll get an RCRA ratio, it sounds fine. Okay, this job rated 2.5 and this other job's 0.75. But if you get close to that denominator, say that 54.3, say if we had a 52-pound force, what that does is it really inflates the recovery time. So you could wind up having a ratio of like 400, which doesn't really make sense. It makes sense to me because I know where it came from, but if I'm showing these metrics, say to a plant manager, and I've evaluated 8 jobs, and I have this one rated a 1.2, this one's a 3, and I have this other one over here that's 500, that's kind of off the chart. So that's one thing that's problematic about the ratio. And if you hear the train, I'm very close to the train track, so I'll pause for just a second. And I'm trying to select question. Oh, here it is. Well, anyway, thank you for relaying the question to me. I'm having a little trouble pulling the questions up.
Yep, that's no worry. That's my job.
Okay. So we take that. You see, we have the durations of the force, the calculated recovery time, and we put those in a ratio of the model recovery time. If you look at the bottom, the RCRA ratio is basically a sum of those recovery times. You have to keep track if some have a frequency more than one, you times that frequency. You can see the equation there, but it's basically the model recovery time divided by the actual. And of course, your actual recovery time would be your cycle time minus the segments during that cycle where you're actually applying force. So you can see how that's calculated. And you see the RCRA ratio. Here it's 0.85 and it's less than 1. Now, new metrics, like I was telling you, that question about that E, like I said, when you approach the maximum strength is where recovery time just kind of goes through the roof. And if you exceed that, the maximum population strength, it's infeasible calculation. But before I get to that though, here's two metrics that I've done some work with. One is the surplus and deficit recovery time, and then I'll talk about percentage of workers fatigued next. But this, you can see the surplus deficit recovery time. The example we just worked where we had the ratio was 0.85. The calculation for the surplus deficit recovery time is your recovery time actual minus your recovery time model. So those are the numbers we just came up with. The 21 seconds was your actual recovery time when you weren't applying force, and the 17.2 seconds is what we calculated, times 60 divided by the cycle time. Now that looks kind of, you wonder where does that come from? And actually that 60 divided by the cycle, I've condensed it a little bit because you start out, you have 3,600 seconds in an hour. So you divide that by your cycle time. And in this case, it was 24 seconds. And then you make a correction to divide it by 60 so you can convert it to minutes. And so, but anyway, it turns out to be 60 divided by cycle. But that gives you surplus or deficit recovery time. So if it's positive, that means over an hour of doing that, if you look at the pie chart, you would have more recovery time than you needed over an hour. If it was a deficit, it would basically mean that there was not enough recovery time. So it would be a negative number. Now, these are, when you're looking at these, you realize it's really, both metrics are one and the same. It's just a different version of one's a different version of the other one. That ratio is, if it's green, if it's 1.0, that's the point where it's surplus and deficit is 0. It's perfectly balanced. Your recovery time, model recovery time equals your actual. If it's yellow, that's the point where it starts to be negative. And here's potential application for that. It kind of gives you a way when you're comparing jobs. Say if we were looking at rotation, and I know rotation is not a solution for a high-risk job, but if you're rotating and you have, say, moderate risk jobs, or maybe you have one job or station that's maybe marginally high risk, rotation is a way to balance it out. And at least in some, if you're going to rotate anyway, it makes sense to try to optimize it. But you can see where you have each station, person works an hour at each station, and you have a surplus or a deficit. So the +6 means there's more recovery time in that station in an hour than you need, 6 extra minutes. Station 2, negative 18 minutes, so you're 18 minutes short. Well, you can keep a running log. So we have +6, and then after the -18, we have -12, and then we have +2, so we get 2 back, and then we have +15 on station 4. So through that rotation sequence, we wind up after 4 hours with +5 minutes. We have 5 minutes more recovery than we needed. Now, I know that's not, that's questionable to some degree, but I think it's more reasonable than just rotating without using some kind of basis for the rotation. For example, if we didn't have that station 4, if we rotated into another job that had a negative, we would have a further, go into the hole with our recovery time. Okay. The percent females fatigued is a metric. Now, this is an interesting metric too. you can see for the left hand, it's 19%. If it were 25%, that's a point where the RCRA ratio is 1.0. That's at the point where the model recovery time is equal to the actual recovery time. It's balanced. But if you start to not have, if you have insufficient recovery time and it's imbalanced, if you don't have enough, it starts to get into yellow. And of course, the more excess recovery time you have, it would be green. But this is a way to look at jobs and kind of assess. And then what this metric prevents is the model blowing up and you getting a non-feasible calculation. And I know, I think Jim typically handles it. He's heard him say that you look at each task in isolation, and if it's unacceptable, then you know your total is not going to be acceptable. But this is a way that you can see, okay, what strength level would be needed to do this with sufficient recovery. And all this is doing is changing. Remember that E value is playing around with that population strength from 1 percentile up to 10th percentile. It's actually an algorithm. You can do it with a do loop in software. I have to do it both ways. I have that. And also I have an Excel calculator that it actually calculates, I believe it's like 2,000 or 3,000 calculations, depending on how many tasks you have. And it goes and finds the point where it's balanced. But anyway, that's a way to put the metric in perspective rather than and I found percent females fatigued. But one thing I found out, even the difficulty with that metric is like, well, what about the males? You know, that would be asked by an engineer or supervisor. And so one thing, a recent project I've worked with is consolidating the population strength, the mean and standard deviation, and have percent workers fatigue, and actually factor in the percentage of, kind of like they do with dimensional anthropometry, when you combine populations. And I do it factoring in the percentage of males and females. So if there's a higher percentage of female workers, it's going to be a little bit lower. The mean's going to be lower, but it factors in, it comes up with one mean and standard deviation. So now I can present the data. Now, still think ideally the 25th percentile female is where we would design for, but there's a lot of, I guess, misunderstanding or being not unintuitive, that I think there's enough benefit gained in people understanding the metrics that they can say, oh, okay, this metrics Murray's provided, if we're less than 25% of the workers fatigue, that's good. And if it's, you can see if it's yellow or red, it gets higher. But I found that to be a useful metric versus the alternative, the model blowing up and not being able to provide a metric, or having to tweak the numbers or something, or having to present it, a ratio that's 400 or 500. This seemed like a good solution to that. Now, application barriers. One, I think, is basic understanding of the normal distribution. But again, if you don't get too deep into the normal distribution, but that helps to understand that. Access to population strength values, access to posture modifiers, and then we'll talk a little bit about force measurement requirements and accurate measurement of force duration, and understanding kind of how to put it all together. But as far as population strength values, I actually started with a spreadsheet, and I take the different research papers or textbooks, and I just put them in a spreadsheet so I could find them, and then deciding, hey, which ones am I going to use? And typically you want the ones that would most, the age range maybe would be most representative of the workforce, and the most recency too, is it an old study or a new study? But since then I've worked developing an online database, and should by the end of this summer, the fall, kind of got diverted in working on my anthropometric database stuff, but I'm going to have an online database so practitioners can more readily find this kind of information. And I have one that some Auburn computer science and software engineering students put it together, and we have it working for the torque and turn values, but we don't have it have that completed. Now here's another thing: posture modifiers, and it could be, for example, if everyone's You've probably seen in a textbook or something, if your wrist is bent, extension or flexion to different degrees, what percentage of your grip strength you lose. And there's also posture modifiers, though. It's based on the types of force. For example, there's certain types of pinch grips that they have modifier. You can find research papers where they did research for that particular force type to determine what the modifiers were. For example, with grip span. So when you're evaluating the work, that's another thing you take into account is the modifiers, because under ideal conditions, under the ideal posture, wrist straight, optimal grip span, you have one strength. But if you're less than ideal, for example, if your grip span's 4.5 inches, your modifier would be 0.57. So you would lose about half of your strength. You'd only have 57% of the beginning strength. And that's one thing in your calculations that when going back to that E value, that population strength value, you would multiply that by this modifier to reduce that number, to take into account the awkward posture. Okay. Another thing I think intimidates people a little bit is there's a tremendous need to accurately and efficiently measure forces. I know it intimidated me because typically, say if you're looking at a hand-intensive job and then you're using the strain index, well, you only have one input. You only have one force in the model. It's a single task model. So, you're not going to worry if you you're going to use the average force, the worst case force anyway. But in this multitask evaluation, you really need to, as accurately as you can, measure all the forces. And because you can see the contribution of the different tasks that are being performed. So during multitask evaluation, you have a lot of different forces, and some forces are difficult to measure. And I've looked into ratings of perceived exertion, basically subjective force ratings. And a problem with that, it takes so many, you would need somewhere roughly 5 to 7 subjective ratings to account for the differences in people's strength levels. Because you might have one person says it's a 6 and another person says it's a 2 on a 1 to 10 scale. So I'm working on the technologies to accurately be able to take data from, say, 2 people. But to do that, and I normalize the calculator for their predicted strength level. But that's something I'm working on there. Could do a whole presentation on that. It's kind of an interesting thing. And anyway, I'll skip past that. Future applications. One thing I'm working on is ergonomic control panel. And I think there's a lot of potential. If you think about over the time spectrum, like how a lot of companies, so we've got where we are now, but typically if you go back in time, they've done completed risk assessment. Maybe it was last year, 2 years ago. That's like a static snapshot in time. But things change. They have the operational parameters change, line speeds change, make model mixes change. And so you have this static snapshot, and companies try to, every 2 or 3 years, they'll try to update their risk assessments. By the time they get them updated, it may take 6 months. And then they're still, the minute they're updated, they're not say obsolete, but they don't improve over time. Things change and they become, you have some obsolescence there. So looking at more continuous metrics, and if we accurately make changes as process changes are made to the job, or if we're going to make adjustments to operational parameters, we can keep things current. But even more than that is forward-looking metrics. Say if sometimes you'll have a question, okay, what if we go from an 8-hour shift to a 10-hour shift? Or what if we increase the line speed, say instead of a 90-second cycle, what if we go to an 82-second cycle? What's the impact going to be? And that's the kind of thing you really can't answer it. The way we've been doing things for years, you can't answer that quickly. But we don't really take advantage of the digitization of everything. So one thing is the ergonomic control panel concept. And this is where you can make adjustments for the shift duration, cycle time, if you're going to speed up the line, or changes in make model mix. And it would cascade through the calculations, and you could say, oh, okay, here's what's going to happen if maybe next week we will run at 40% of Model 1 and 60% of Model 2. I know in automotive, sometimes maybe sometimes the one model will have a heavier, say a heavier wire harness, or a little bit more force to do some of the tasks, even though they're typically fairly close. But anyway, it's a way to see forward and predict when we're going to have problems, because so many times we make changes, and then after a few weeks we start to experience injuries. And this is a way to kind of proactively, through kind of a simulated forecast, you can see what changes to operational parameters are going to have to your metrics. And then for questions, another thing, I'm doing another problem or thing I'm looking at is a rotation path. I think we think too much in terms of, okay, this job, or say we have 4 stations, the risk at this station, this station, this station. Really, it's not the stations, it's the person's path, the path people take. Maybe I work, 2 hours here, 2 hours here, and then I go work 2 hours over here. Their exposure is really their rotation path. And so I think we need to better model the rotation path. And it's good for design purposes to look at the risk of each station or the rating of each station. But we need to get better at looking at the paths that people work and make sure that their cumulative exposure, especially now that we have the tools with, I know like Auburn University fatigue failure tools in particular, it's a cumulative exposure dose over the day. So you can look at metrics, and then there's ways with RCRA you can kind of approximate that. You can look at the duration of the shift. It's like a grand cycle, and then over the course of the shift, have you exceeded your in-task recovery for 8 hours? Okay, but that's the presentation. Questions?
Great. Well, thanks, Murray. Again, really, really makes you think. Like you said, this whole fatigue thing and how it accumulates, and are we getting enough rest in between? A challenge for anyone doing ergonomic assessments. So, thank you for even just getting us to think on that. So, I think you had a great slide on there, which was your barriers, because that's where our first question was really coming from. Is that database of the maximums? Because if you're going to have to calculate a recovery, you clearly need to have an idea of some of the maximums. Are you, I guess, it's, you said your database might be ready by the end of the summer. Are you going to make that public and maybe be able to share that with us? And until then, do you have any other thoughts on where you're collecting those maximums that we can use in the RCRA?
I would like to have something that at least some version of it is free to people on the website, where they can get the basic information. There may be a more advanced version that's a subscription model, but I'm not sure about that. But anyway, what I find though is I've applied the RCRA. You develop, it's based on need. Okay, I see this job. There's some force I don't have data, or some type of finger force I don't have data for. And so I can look in the textbooks I have, or now as a student, it's very easy to locate research papers, and I can find papers that have the data. But when I was back in the industry, you're just kind of out of luck. If it wasn't in the handful of papers I had or in a textbook, there wasn't an easy way to find that.
Okay. And on that note, we had a little chat sidebar, teaching these days, and when we teach the RCRA, we use Jim's hand pack software, has a lot of collection of that. So, I just sharing that is where I use a lot of the hand ones. But that kind of leads me to one of the questions I had. When we're talking muscle fatigue, we really do have to remember it's about a muscle. So if the tasks is a grip force, and then the next element that they do is an overhead, and that the muscle that they're really fatiguing is a shoulder one, I kind of look at it as I do an RCRA for the forearm muscles, and then I do a second RCRA for shoulder, because you may be fatiguing a different muscle, which has then a different force and then a different duration. And really, the hand activity will really be a recovery for that shoulder potentially.
Mhm.
So I guess, that's kind of one of the things with the RCRA is you got to remember your background here. It's fatigue. So you got to do it by muscle group, not just by job,
And
right?
if you're looking at the shoulder, probably like let's say when you go work out, you're pushing or pressing movements like your forward flexion or your adduction, things that we know that is coming away from the body. That might say we're looking at the right shoulder, and then you also have things like the pulling, like pulling down or pulling toward you. So you might break it into two different groups there. Now, one really, I should have mentioned it. Paper Nick Ladelfa and Dr. Potvin on arm force calculations is a tremendous technology. If you know where the hand is in relation to the shoulder, there's a simple version that you can calculate the population strength in each of the 6 primary directions. And there's the second paper, though, the more complex one, you have inputs from 3D SSPP. I don't use that as much, but it takes a lot more time. But you can, that's one good way for general arm forces where you're a directional force. You can calculate that and use that for your shoulder data. Other things that are kind of interesting is with a lot of times in material handling tasks, we overlook grip strength. And so, and what people are finding in application is we're running out of gas with the grip strength before we are with the torso or the shoulders. That's another thing.
Yeah, so I think a good policy is just be aware that you have both muscles active and you really do the RCRA on both. And I would reiterate exactly that when I do a shoulder RCRA, I use the arm force field is a great way of getting that maximum again, one of those barriers, because you need to know the maximum in order to determine what percentage of the maximum you're working for at a specific duration.
And I've grown to appreciate too the subjective force estimation. One of the benefits there, because the conventional approach, like I showed, you have to have a population strength, and then you adjust with modifiers. But with subjective rating, the modifiers built into it. You know if they tell you, oh, this is a 4 on a scale of 10 and their wrist is bent, it sort of takes into account the posture as well. And two, there's a lot of things, some jobs, there's some forces that you can measure and just some that are really difficult or it's going to be time consuming. Not that they couldn't be measured or with a more advanced technique, but a glove or sensors or something. But to economy of scale, I found that using subjective estimation to complement things I can just take a force gauge and measure really helps things, speed things along.
Yep, I think that's a whole WebEx in and of itself. We've had lots of discussion about, force estimations and force replications and perceived exertions by operators and even their motivation. But yeah, so maybe I'll have to find some good webinar talkers about using force estimation, because that definitely is something that anyone out in the field knows that sometimes it's very, very difficult to get the exact measurements and then also find those maximums. So you're right. Some of the force estimations, or at least can be part of your RCA kind of evaluation. Any other questions then? Please feel free to come off mute. I think sometimes the presenter, Murray, it's hard to talk to just your slides and not see all the wonderful faces of everybody listening in. So please come off mute if you have a quick question, or if you feel more comfortable, please give us you can type it in.
And anyway, it seems like I enjoy helping people when they run into difficulties. A lot of what I learned, I run into problems and I had to figure out solutions. And sometimes I'll look at a research paper, or I'll ask Jim. There's some other people. There's probably a handful of people that apply RCRA, Ben Zavitz, is another person. Um, anyway, I, if people have run into problems and it's something that you just can't get your arms around or figure it out, don't hesitate to give me a call, because a lot of what I learn is through other people and their problems, and I need to figure that out too. And if somebody's having the issues with something, I need to know it so I can avoid that, or know how to handle that, or prevent others from running into that problem.
Yeah, I think, and I would even vouch for that. Murray is great at having those good discussions about, okay, this didn't work for me the way I thought it was going to be. So I like to see that. And that's a nice way to even end this, is that, we are networked of ergonomists together. Let's use each other in a nice way and have great conversations about that. So thank you, Murray, for joining us today and having the discussion about the RCRA. And we'll make sure that this recording will be on the ACE website, and also make sure we have some contact info on how to get a hold of Murray, and we'll keep you posted if we get even some databases set up on that. So thanks again, Murray, for sharing with us today.
Thank you, Allison.